If you look today where our raw materials come from, you'll see that we can source raw materials from basically anywhere in the country, which is really important because we're looking at regional distributed manufacturing systems. Today we're located in New York, and we use lots of buckwheat hulls, which are of great abundance within western New York. And since we have a thriving paper industry, we use materials such as cellulose sludge. Most manufacturers of paper currently pay to have cellulose sludge discarded. We can take this low-value waste and convert it into either protective packaging or structural cores for things such as furniture. What's nice about buckwheat hulls, however, is that we're currently looking at putting our third facility in Texas. Now, Texas has a lot of rice hulls. It's a great analog for buckwheat hulls, for example. And in Indiana, we can use oat hulls. No matter where we're located within the United States, we can easily source agricultural waste that'll give us the same performance characteristics no matter where we're located. We have a great relationship with the USDA, and we've worked with everything from lobster shells in Maine to hazelnut husks in the Northwest. And we can get the same quality product out each and every time. What's interesting about this process, however, is that it's highly scalable and distributable. If you look both at Europe as well as Asia, you'll see that these same materials are found throughout the world, meaning that we can continue to distribute this technology as well as this platform to manufacture the same environmental technologies no matter where we're located. Next, what I'll show you is a quick video of our manufacturing from a year ago today. We've only been manufacturing since about mid-2010. This will give you an idea of how our process works. We take our ag waste, we steam pasteurize it. We are taking materials that are derived directly from the field, so they have a really high bacteria and fungal load on them. We clean them up, and we introduce our tissue culture. Once the tissue culture is applied, we put it in a tool, which gives it its final form. And once the lid goes on the tool, this is where the magic really starts to happen, because that tool provides its own little microenvironment for the fungus. And that's where the fungus starts to self-assemble the material, driving all energy that it needs for growth from that agricultural waste. If you go into our manufacturing facilities today, we don't look like a traditional manufacturing facility as much as we look like a vertical farm. We have racks and racks of growing materials. Our process time is only on the magnitude of 5 days, and once complete, they're boxed up and shipped out. Now, I've said a number of times already that we grow materials, but I'm sure that's fairly difficult to visualize because when most people think about growing materials, they think of trees or they think of plants, things that require either months or years to grow in order to get the desired material characteristics out. But we literally do grow our materials in 5 days. So this is a time-lapse video that I'm going to start right now. And what you'll see is a number of white little specks. And that's the initiation points of that fungal mycelium to start growth. It starts to radiate out, digesting some of the particles, that's where it gets all of its energy from, while binding the rest together. And after that 5-day process, you're left with a very rigid and solid material. Our final step is a drying or an activation step. This allows us to remove the remaining water. Our process is very similar to concrete, where we have to mix water into the process and then pour it into a tool. And of course, it inactivates the fungus. We never have to worry about the fungus growing ever again. We export to a number of different countries, including Australia, so it's really crucial that we don't have any living material left in our product. So that's one of our primary QC checks. And then it's ready to go out to our customers, where today we work with a number of Fortune 500 companies, packaging everything from heavy objects such as furniture, things like tables and bookshelves, to consumer electronics and appliances. One of our customers is Steelcase Furniture, for example. Steelcase is a great example of one of our customers because they came to us early on because their expanded polypropylene that they were using, first, was fairly expensive, but second, wasn't performing. They weren't getting the protection that they needed out of the foam parts that they were using. I'm glad to say that our materials were the first materials that they tested that passed all of their tests on the first try. It gives them better performance than what they were seeing out of foam, but of course, it's also sold at the same price point. Remember, we use waste as our raw materials, and we're not tied to just one line of waste. So our price isn't coupled directly with just one material. Next, we ship Dell's servers. Dell Computers is a great example of one of our customers because they were using hand-fabricated foam. There's quite a bit of labor going into these because of the pricing of a tool that's required to manufacture expanded polystyrene. Remember, there's a lot of high heat and high pressure that goes into these systems. It didn't make economic sense for them to buy the tooling to make the foam parts. Since we literally grow our materials at ambient conditions, our tooling costs are literally less than a tenth of that of a typical EPS part. So we can provide them with a quality product at a lower price point than what they're paying for the foam today. So of course, today we're working in protective packaging, but our materials have a number of other key characteristics that set them apart from foams, either making them comparable to foams or even better. For example, our materials are great in terms of insulation characteristics. They're the same type of thermal insulator that you'd find in terms of expanded polystyrene, and they're great for sound attenuation or acoustical tiling. Another great benefit of our technology is that it's a Class 1 firewall. You can hit this material with a blowtorch, and it doesn't burn. That's something that you would never be able to get out of something that's synthetically derived from natural gas, for example. Those materials ignite pretty quickly. And one of our greatest advantages that we see is that the material is 100% home compostable. Once you get your protective packaging material in the mail, you unbox your Amazon package, you can put this material right into your plant-based compost pile. And within 30 days, it's going to passively return to the earth. But if you're located in an urban area, and you don't have access to a compost pile, you don't have to fret. You can just put it right into your municipal landfill, and the anaerobic microbes that live in your landfill will break down the material in 45 days. Now, when Eben and I started the company in 2007, we were just two students right out of Rensselaer Polytechnic Institute. We didn't have the Class 10,000 clean rooms we have today, or a production facility, or the nice laboratories. We were just passionate about doing something to really help the environment. And we saw that the material that we had come up with had a significant market opportunity. See, the first materials that we made, we mixed in our kitchens. We didn't have expensive incubators, but we had the nice dark conditions that mushrooms like under our beds. So we grew our first materials in our apartments. Since we didn't have access to great equipment, we just contacted the National Institute of Standards and Technology, and they were nice enough to let us come down and use their equipment. And we tested our materials for things like insulation characteristics and thermal characteristics. And we found that we had a product that could compete, at least in regards to physical properties, with EPS. Armed with that information, we were able to go out to business plan competitions, where we won competitions such as Oxford and the ASMEI show. But we also put in applications for grants to continue to develop our technology, because right now it was a really early stage. We might have been working on this product for about 3 months at this time. We didn't really know where the ideal market applications were. We got our first grant from the National Collegiate Inventors and Innovators Alliance, which helps foster entrepreneurship within the collegiate setting. And of course, one of our biggest grants that we won was through the Small Business Innovation Research Program through the US EPA. And that's really what helped get us started. And we transitioned from an office to a dilapidated basement. And you're probably looking at this and you're saying, wow, okay, why would you move from a fairly nice office to a basement where ceiling tiles are falling out? Well, this basement gave us a number of things that we didn't have in the office environment, in the business incubator where we were located. First, it had a lot of space. And of course, it was dirty space, but we were starting to expand and grow more materials, and that was space that we desperately needed. But it also, since it was a print shop, had an old dark room. And this dark room had a sink, it had a chemical hood, and it saved us from walking up 2 flights of stairs every day from our office to the kitchen to get water for all of our experiments. It was great cardio, but didn't really help with conserving time. With our new laboratory space, we started to produce more samples, starting to go out to customers, potential customers at this point, and seeing if they would like to purchase the product that we had. A number of iterations later, we were ready to start manufacturing. We hired our first manufacturing engineer and went on to win a $500,000 business plan competition in the Netherlands.